Good morning, students. Am I audible? Okay. Today, before we are going to our next unit, next chapter, we are going to discuss about momentum equation. Okay. So before we move on to our next chapter, that is uniform flow, we are going to discuss about momentum equation. Okay. So that momentum equation is based on our Newton's second law. Okay. So here you can see our momentum equation is based on Newton's second law or second law of motion. So that second law is, we all know, the summation of force under consideration and is in the direction of flow. Okay? If you see in this figure, when you take the summation of all the forces, these all forces should be in the direction of flow. Okay, should be in the direction of flow. Okay? And is equal to the change of momentum in the same direction. Okay, so here we are going to derive the momentum equation. Okay, so this is the figure. In that figure, we have considered two sections. One is section 1 and one is section 2. One is section 1 and one is section 2. Okay. We have considered two sections, and obviously this is your uniform flow, uniform steady flow. When we are considering for derivation of momentum equation, that flow is uniform and steady flow. And steady flow. Okay. So this is your section 1 and this is your section 2. Okay. So here we have considered the velocity at first section is v1 and velocity at second section is v2. Okay. Then pressure at first section is p1. Okay, and pressure at the section 2 is p2. Okay. So definitely there will be a slope, as we all know the water is flowing from a higher elevation to the lower elevation. That is why we have a slope, and that slope is theta. We have considered as theta, or we can also say that this theta is our bed slope of the channel. Okay, so we have considered that slope is theta. Okay, and the distance between first and second section, we have considered that it is x meter. Okay, so definitely, suppose this is your reference line, or you can say datum, and perpendicular that datum, we our weight of that particular mass, particular water present between the first section and second section will act perpendicular to this datum line. Okay, so it's not perpendicular to the bed of the channel. Okay, or bed of the river. It should be perpendicular to the reference line. Okay, as our bed of channel is not parallel. Okay, we have some slope. Okay, as we all know, in open channel, the water flows from a higher elevation to the lower elevation. Okay? So whatever the water present between the first section and second section, the weight of the that water acts perpendicular to the datum line. Okay. So if we consider to the bed of the channel, with respect to the bed of the channel, then we have to resolve into two direction. Okay. So these things you already know. as this is your W is nothing but your weight of the water. So if you resolve into two direction, one is cos theta and one is sin theta. Okay, okay. And then definitely we have some frictions at the bottom of the channel, and definitely the direction will be in opposite, as that friction is a resisting force. It is not going to enhance our movement, it is going to restrict our movement. So that is why our friction force or friction factor, it is in opposite direction. Okay, you can see here the velocity is in this direction, discharge is also in this direction, or you can say this is the direction of flow, this is the direction of flow. So that is why our friction is in opposite direction. Okay, okay. So now we have to use Newton's second law of motion for momentum equation. Okay, so the summation of all the forces in the direction of flow. So first we come here. The first one is P1. Okay, pressure at section 1. Okay, okay. Then if we consider pressure at section 2, it is in opposite direction. That is why it's negative. Okay, we all know that thing you have already studied in third semester, that hydrostatic pressure it always acts like this. Okay, in a triangular form, Okay, okay. If this is a triangular, it acts in this direction. If this is a triangular, it acts in the other direction. So that is why your P1 is positive and P2 is negative. So that is why P1 minus P2. Okay, so first is P1, then we have negative, then we have considered the next force, that is P2. Then we have in the direction of flow. Okay, we have a component called W sine theta. Okay, and it is in the direction of flow. Okay, so that is why it is positive, W sine theta. Okay, sine theta. Okay, then we have, again we have friction factor, and it is in opposite direction. That is why it's negative. Okay, friction factor, okay, is equal to rate of change of momentum. We all know momentum is mass into velocity. So that is why mass into velocity, when we are talking about change of momentum, that is initial momentum minus final momentum, or if you say that velocity v2 is greater, then you can write in this way. Okay, and we are talking about change of momentum, so it are changing with respect to time. Okay, so you can say rate of change of momentum. Okay, so you can take mass common, then v2 minus v1. Okay, divided by time. Okay, so mass we all know, weight equal to, forget about weight, density. Okay, density equal to mass by volume. Okay, volume. Okay, density equal to mass by volume. So in place of mass, We can write density multiplied by volume. Okay, density multiplied by volume. So in place of mass, we substitute density multiplied by volume. Okay, V2 minus V1. Okay, then we have divided by time t. Okay, so that first part will be P1 minus P2 plus W sine theta minus friction factor. Okay, is equal to, in place of mass, we are going to substitute density multiplied by volume. Then we have V2 V2 minus V1 divided by T. Okay. So volume is nothing but your meter cube. The unit of volume is meter cube. Okay. Volume, the unit of volume is meter cube. And time, if we consider second, okay. So meter cube per second, you can write distance. Okay. Okay. In place of volume by time, that is meter cube per second, we can write discharge. Okay. And what we are going to do, we are going to multiply it by acceleration due to gravity in the numerator, and in the denominator also we multiply it by acceleration due to gravity. Okay. So rho into g, density multiplied by acceleration due to gravity, we can write specific weight. Okay. Divided by this g, acceleration due to gravity. Okay. Multiplied by q and v2 minus. Okay. So you are going to get this expression. Okay. That is P1 minus P2 W sine theta minus friction factor is equal to specific weight divided by gravity multiplied by discharge multiplied by V2 minus V1. That is your velocity at section 2 minus velocity at section 1. Okay. So this is the derivation of your momentum equation. Okay. So here it is directly given the equation. The derivation is this. Okay. First, we have to take the change rate of change of momentum. That is change of momentum divided by time. Okay. So momentum, we all know, mass into velocity. So mass into initial velocity minus mass into final velocity. Okay. So you can take V1 minus V2 or V2 minus V1. It doesn't matter. Okay. Which one will be greater? It will be, so mass, in place of mass, we have taken the equation of density. That is density equal to mass by volume. So in place of mass, we can write density into volume. Okay. So volume divided by time, that is the unit of volume is meter cube. Time we have considered second. So meter cube by second is nothing but our discharge. So in place of this volume by time, we have substitute discharge. Okay. And what we did, we multiplied acceleration due to gravity in the numerator as well as denominator. Okay. And we know rho into g is nothing but your specific weight, and g is left out, so it will divided by g multiplied by q v2 minus v1. So this is the equation of momentum equation. Okay. Okay. If you have any doubts, you can ask me, or if you don't have any doubts, then we will move on to the next chapter, that is our uniform flow. So we move on to the next chapter, that is our uniform flow. Okay. So I think we have already discussed about uniform flow. So flow is nothing but if you have a channel, if this is the bed of the channel, if you consider two section 1 and 2, suppose this is 1 and this is 2. Okay, this is the level of water. So if you measure here, depth of flow, discharge, velocity, and then you travel some distance x. Okay, maybe 100 meter, 200 meter, 1 kilometer. It depends on you. Okay, you travel some distance and you consider another section 2, and at the same section again you are going to measure the same parameters, that is your depth of flow, discharge, and velocity. If all the three parameters in both the section are same, then we can say the flow in that particular channel is uniform flow. Okay. So here you can see in this diagram or in this figure, we have considered two section 1 and 2. Okay, so here we have measured y1, okay, at section 1, v1 and q1. Then we travel some distance and we consider another section 2, and then we measure the same distance at y2, v2 and q2. Okay, if all the three parameters are same in both the section, then you can say this flow is uniform flow. Okay, so what we are going to do here, then we are going to apply Bernalillo's theorem. Okay, so Bernalillo's theorem, you have already studied about Bernalillo's theorem. Anyways, we are going to discuss again. So here for first section, we are going to find out the total energy. Okay, we have already discussed about total energy. The total energy is equal to kinetic energy head plus potential energy head plus datum energy head. Okay, so that is why we are applying Bernoulli's equation at section 1 and 2. So for the first section, if you find out total energy, we'll be having kinetic energy head v1 square by 2g. Then we have potential energy head, and at last we have datum head. Okay, is equal to, say, the total energy of section 1 should be equal to total energy of section 2. Okay, or you can say that section 1, total energy of section 1 and total energy of section 2 should be same. Okay, so here again in second section is equal to your kinetic energy head, potential energy head plus your datum head. But due to the friction, as the water is flowing from upstream to downstream, due to this friction there is some loss. Okay, that is called head loss due to friction. Okay, head loss due to friction. K is equal to constant. Okay, so these two total energy at both the sections should be same. Okay, so that is why in second section, from first section when the water flows towards the second section, and when it reached the second section, at a time it lost some energy due to the friction at the bottom of the channel. Okay, so that is why that loss is called head loss due to friction. So we have to add losses to get the equal total energy with respect to your section 1. Okay, so that is why if you see in this equation, total energy at section 1 is equal to total energy at section 2 plus loss. Okay, so this Bernoulli's equation is applicable not only in uniform flow, in others flow also it's applicable. Okay, but see, as we are considering uniform flow, our depth of flow at section 1, or depth of flow at section 1 is equal to depth of flow at section 2. Okay, because of the uniform flow. Okay, so velocity at section 1 is equal to velocity at section 2. Okay, okay, so that is why this y will be cancelled out. Okay, This y will be cancelled out because both the depth of flow for both the section is same. The velocity is also same, so you can cancel out this term also. V square by 2g. That is kinetic head. So what is remaining is your Z1, that is datum head at section 1, minus Z2 datum head at section 2, or you can see here equal. Okay, Z1 is equal to Z2 plus head loss due to friction. Okay, head loss due to friction. Okay, Z1 is equal to, that is datum head at section 1 is equal to datum head at section 2 plus head loss due to friction. Okay, so you can bring it in the left hand side, so it will be Z1 minus Z2. You can write dz. Dz is change in, this is your dz. Okay, change in datum head. Okay, change in datum head, that is your z1 minus z2. Okay, that is your change in datum head. So always remember, in your open channel flow all the slopes are same. Okay, if you consider bed slope, if you consider friction slope, or you consider surface slope, surface slope is nothing but your water surface slope. Okay, so all these slopes are same only for uniform flow. Okay, this is applicable only for uniform flow. So bed slope you all know. Okay, friction slope we have already discussed, and this is your water surface slope. Okay, a slope, this slope is nothing but your water surface slope. So all the three slopes are same for uniform flow. Okay, so here we have used momentum equation for open channel flow. You can see your velocity is same, pressure is also same. Pressure is same because our depth of flow is also same. Okay, as when we talk about pressure, it depends on the depth of flow. Okay, that triangle, it depends on the depth of flow. Its depth is more, then your triangle will be greater. Okay, so as the both the depth is same for both the section, so that is why our hydrostatic pressure for both the section is same. Okay, that is why this will be cancelled out, and what will be left out is w sine theta, because this will be 0 when v2 and v1 is same. So this will be 0, 0 multiplied by something, again it will be 0. Okay, so what will be left out is w sine theta minus friction factor. Okay, or you can write this expression. So this expression is only valid for your uniform flow. Okay, so next topic is your Manning's and Sage's formula. Okay, so I think these two formula you have already studied. So in open channel flow, we use this formula to find out the velocity. Okay, to find out the velocity of flow. Okay, one is Manning's formula. It is very common and widely used. The formula is nothing but 1 by n r to the power 2 by 3 s to the power half. S is nothing but your slope. R is, we all know, R is your area by weighted perimeter. So R is nothing but area by weighted perimeter, and N is nothing but your roughness coefficient. Okay, N is nothing but your roughness coefficient, or you can say Manning's coefficient. Okay, and Similarly, we can use Sage's equation also for calculating velocity. Okay, that v is equal to c root over r into s. Okay, s is nothing but your slope. R again its area by weighted perimeter. You can see here. Okay, hydraulic radius is equal to area divided by weighted perimeter. Okay, and c is your Sage's constant, or you can say Sage's coefficient. Okay, so don't worry. This the formula we are going to use in this chapter to determine velocity. You can write down this expression. Okay, so this is not in your syllabus, but when you go for competitive exam, you can find this relationship. Okay, the relationship between Sage's constant, Manning's constant, or Manning's coefficient, and friction. Okay, so here is the relationship. You can write down this relationship. Okay, the derivation is not required, but the relationship is important. That is, c is equal to 1 by n r to the power 1 by 6 is equal to root over hg divided by friction factor. Okay, so this is a relationship between Sage's constant, Manning's coefficient, and friction factor in open channel. Okay, the small f is nothing but your friction factor. Okay, okay, so you can write down this expression. That c equal to 1 by n r to the power r 1 by 6 is equal to root over hg by f. Okay, r is hydraulic radius, that is area by weighted perimeter. G we all know that acceleration due to gravity. Then next topic is your economics section. So this thing is self-study. Okay, we have already studied in details about the economic channel section. So here we are going to direct see the derivation for economic channel section. You have studied in third semester, third or fourth semester, I don't remember, but you have studied. Okay, so here we are going to apply this economic channel section. Okay, we are going to apply. So here you don't need the derivation. Okay, but you should know what will be the width of, or you can say what is the formula for economic section of a rectangular channel. Okay, so you should know about it. Okay, so this economic section topic is self study. Okay, this is self study. Okay, study of your own. Okay, you can follow your notes also, or third semester or fourth semester, or you can follow any books. You can also follow that hydraulic and hydraulic machine by R.K. Bansal. Okay, you can follow that book also for that economic channel section. One is trapezoidal, rectangular, and triangular channel. Okay, these three are most important. Okay, rectangular, triangular, and trapezoidal. Okay, as per concern to your open channel. Okay, So we are going to solve the first numerical related to your open channel. Okay. So you can write down this question that find the discharge through a rectangular channel of width 2 meter having a bed slope of 4 in 8,000. Okay. The depth of flow is 1.5 meter. Take n equal to 0.012. So what we have to do, we need to find out the discharge where the width of the channel is given 2 meter and bed slope is given 4 by 8,000. Okay. So this is your rectangular channel. Given is 2 meter. Width of the channel is 2 meter is given. Y value is 1.5 meter is given. Manning's coefficient is given 0.012. Okay. So these are the given parameters and we need to find out the discharge. Okay. Q. We need to find out discharge. Okay. So here the solution is already here. Area is B into Y. Definitely that is a rectangular channel. That is your width of the channel multiplied by Y. Depth of flow, you will get the area. Okay. That is 2 into 1.5. 3 meter square. Okay. Then we need to find out the weighted perimeter. Because see, when we are asked to find out discharge is nothing but area into velocity. Okay. Area into velocity. So area we have already calculated. But to calculate velocity, we have to use Sage's equation or Manning's equation. Okay, as in the question, Manning's coefficient is given, so that is why we are going to use Manning's equation. Okay, if in the question the Sage's constant is given, then we are going to use Sage's equation. Okay, so as the Manning's equation is given, so we are going to use Manning's equation to find out the velocity. 1 by n r to the power 2 by 3 s to the power half. Okay, s to the power half. So to find out the velocity we need Manning's constant or Manning's coefficient that is given. Then we need to find out r. Okay, r is nothing but hydraulic radius is nothing but area by weighted perimeter. Okay, area we have already calculated, that weighted perimeter we need to calculate to find out this r. Okay, and s is nothing but slope. So slope of the channel is already given, that is 4 in 8,000, that is 4 divided by 8,000. Okay. Okay, so you substitute in this equation, find velocity, then velocity you substitute in this equation, you can easily find discharge. Okay. So this weighted perimeter, see, weighted perimeter is nothing but the perimeter of the channel up to the level of water. So that is why if you consider the weighted perimeter of this rectangular section, then we have to add this. Okay, this portion, then this portion, and again this portion. Okay, so that is why y plus b plus y, or you can write b plus twice y for rectangular channel. Okay, b plus twice y. Okay, so you can write b plus twice y, b plus twice y. Okay, so here b plus twice y, b is the 2 meter and 2 multiplied by 1.5, that weighted perimeter is 5 meter. Okay, and slope is already given 4 by 8,000. Okay, you can also write 1 by 2,000, it's up to you. Okay, because at the end you are going to use calculator, so you can directly substitute 4 by 8000, doesn't matter. Okay, so definitely our Manning's coefficient is given, so that is why we are using Manning's equation. V equal to 1 by n r to the power 2 by 3 s to the power half. Okay, so this Manning's n is given, so we have substituted here. R is nothing but area by weighted perimeter. Okay, 2 by 3, and slope is given 1 by 2000. It is given 4 by 8000, so you can write 1 by 2000 to the power half. So if you substitute, you can find out, use your calculator, find out the velocity. You're going to get the velocity approximately 1.33 meter per second. Then you find substitute the velocity here, and you can find out the distance. Area we have already calculated is 3 meters square. Okay, so you substitute here and you find out the discharge. Okay, so your discharge is almost 4 meter cube per second, 3.99 meter cube per second. You can write approximately is 4 meter cube per second. So this meeting is going to end. Okay, so this meeting is going to end. So we will start our next class in 11:15. Okay, so there is a 10 minutes break, and we will start our next class at 11:15. Okay, with this same link. Okay.